Good day everyone, my name is Nel Joshua D. Balanga and I would be discussing Hamiltonian Dynamics. So what is Hamiltonian Dynamics? It was first formulated by William Rowan Hamilton in 1833, which contains the principle of stationary action. This principle states that the trajectories or the solutions of the equations of motion are stationary points, known as critical points of the system's action functional. It is advantageous when dealing with a system of small number of particles, such as in the statistical mechanics involving gases, or no particles at all, such as in quantum mechanics. It is a function of position and generalized momentum, not velocity. Therefore, the general equation of the Lagrangian is h as a function of the generalized coordinate q and its momentum is equal to p and the velocity of the generalized coordinate q in terms of q and p minus the Lagrangian, which is a function of the generalized coordinate q and its velocity. For the n coordinates qi, h, or the Hamiltonian, is then the summation of all of the variables involved of p, I, qi, or q dot I, or the velocity of the generalized coordinate, minus the Lagrangian. From our previous lesson, we know that the definition of the momentum, pi, is equal to the derivative of the Lagrangian with respect to q dot. So that is the general equation of the Hamiltonian. So let's try to understand further the Hamiltonian equation. So simply put, we can say that the Hamiltonian is equal to the summation p I q dot I, because remember it's the velocity minus the Lagrangian. Let's simplify first this first term. So p I q dot I, when given to what we usually know, we can express it as p x dot, which is further simplified as p multiplied to the velocity. We know that p is actually equal to the mass times the velocity of an object. So plugging in this equation to this equation, we can say that mv multiplied by v, which gives us mv squared. This looks familiar because it is essentially the kinetic energy of an object. So we know that the kinetic energy of an object is actually 1/2 mv squared. Therefore, we can say that p multiplied by the velocity, or mv squared, is also equal to twice the kinetic energy, 1/2 mv squared. So we can say that this first term is actually twice the ke. Next, let's now investigate the next term. So from our previous lesson, we know that the Lagrangian is equal to the kinetic energy minus the potential energy. Therefore, we can write the Hamiltonian as first twice the kinetic energy minus the Lagrangian, which is ke minus pe. So we simplify that. This becomes now a single ke minus the negative potential energy. So distribute that. We can now say that the Hamiltonian is actually the total energy of the system, because it is the kinetic energy plus the potential energy. Now, using our common representatives, we can say that the Hamiltonian is equal T plus V, or the total energy of the system. So that is the Hamiltonian in its essence. Now it's time to apply the Hamiltonian principle and equations in some sample problems. We have here a sample problem regarding the projectile motion. So using Cartesian coordinates, find the Hamiltonian for a projectile of mass m moving under uniform gravity. Obtain Hamilton's equations and identify any cyclic coordinates. So you might be asking, what are these Hamilton equations? The Hamilton equations is given that the derivative of the Hamiltonian with respect to the momentum is equal to the velocity of the generalized coordinate q, and the negative derivative of the Hamiltonian with respect to the generalized coordinate q is equal to p dot. So you might be asking, how do we get this equation? So let's look at the Lagrangian. We know that the Lagrangian is actually the function of its position and its velocity. Then we know that the Hamiltonian is the summation of q dot I pi minus the Lagrangian. In order to get this, we must now look into the change of the Hamiltonian. So if we were to do that, the change of the Hamiltonian is simply the summation of the I d I plus q dot d pi. So we know this from our multiplication rule, minus the change in the Lagrangian. However, we know that the change in the Lagrangian is actually the derivative of the Lagrangian with respect to the velocity, dq dot I plus dl dqi dqi. So plugging in this equation to our first equation, we can come up with change in the Hamiltonian is equal to the summation of its first term, dq dot I plus q dot I, and the change in di minus, so inputting now the Lagrangian, dl over dq dot I dq dot I minus, because we disseminated, dl dqi dqi. However, we know from earlier that the definition of the momentum is actually the L of dq dot I. So we can now see some terms canceling out. So this one, pi dq dot I, is also this one. So this term minus this term would cancel it out. This would now bring us that the change in the Hamiltonian is simply q dot I dpi minus dl dqi dqi. So that is now the change in Hamiltonian. Now that we have this, let's compare this now to our general form of the Hamiltonian. The Hamiltonian could also be represented as the derivative of dh, dh over dpi dpi plus dh over dqi dqi. These two are now very similar. We have the dpi here and then the dpi here, as well as the dqi here and then the dqi here. Therefore, we can say that the dh over dpi is equal to our q dot, or the velocity of our generalized equation, and that the dl over dqi is equal to the dh over dqi. However, we know from our previous lesson that the dl over dqi, we know that the dl over dqi is actually what you call momentum dot, or p dot. So we can say that the negative momentum dot is equal to dh dqi, or we could say that the negative dh dqi is equal to momentum dot. So we now have our Hamiltonian equations, these two. So that is now the Hamiltonian equations. Let's now apply that to a projectile of mass m moving under uniform gravity. So we know that the nature of a projectile is that it moves two-dimensionally. So let's just say this is the projectile m. We know that it is moving in a parabola, meaning it is moving two-dimensionally, in this direction and in this direction. We can put arbitrary coordinates in this one, but to make it more familiar, we can say that this direction would be the x direction, and in this direction, we could put it as the z direction. So, in terms of the Cartesian coordinate system, remember, the Hamiltonian is actually T plus V, or kinetic energy plus potential energy. So in terms of this Cartesian coordinate system, we can say that the kinetic energy, or T, is actually equal to 1/2 mv squared. However, since we are dealing with vectors, we know that V could be obtained as vx squared plus vy squared, then get its square root. So we can say that it is 1/2 m, not y, remember we're using z, not really y pala. So we can have then, let's just use our usual x dot squared plus z dot squared, square root of it squared. This is simplified, so we know that T is equal to 1/2 mx squared plus z squared. And we know that V is height dependent, so it's mgh. Since our height is represented by z, we can say that it is mgz. So since our Hamiltonian is equal to pi qi minus the Lagrangian, we need the Lagrangian. So with this in mind, we can say that the Lagrangian, remember that the Lagrangian is T minus V, we can say that the Lagrangian is 1/2 mx squared plus z squared minus mgz. And now we need to now get the conjugate momentum. So we know that from our discussion earlier, or the definition of the conjugate momentum is Pi is equal to dl over the velocity. So therefore, we can say that the conjugate momentum of x is dl over dx dot, and dz is equal to dl over dz dot. So with that in mind, the conjugate momentum of x is the derivative of the Lagrangian in terms of dx dot. And since we only have this is x dot, remember that because it's the velocity, since we are doing a partial derivative with respect to the velocities, so we treat this as a constant. When deriving it, that becomes 0, and this is our only term that we have the variables for. So this then becomes the derivative of the Lagrangian, which is 1/2 m x dot squared plus z dot squared minus mgz in terms of dx dot. We treat this as a constant, so 1/2 m x squared plus 1/2 mz squared minus mgz. This is now 0 because we don't have the variable x dot, and we only have this one, which is 1/2 mx dot squared. So we are only concerned with this one. So getting the derivative of that, we have the px as the derivative of x dot squared is 2x. So this cancels out. We are left with mx dot. Getting the conjugate momentum of z, it's the same. This time, this would be ignored, or as well as this one, and this is now our term. So in the same vein, it is now mz dot. We can say that x dot is equal to the conjugate momentum of x over its mass, and that c dot is equal to the conjugate momentum v over m. Since the system is conservative, the Hamiltonian is then given as h. We know that it's p plus v. Then we can say that it is 1/2 m x dot plus z dot squared plus mgz. However, we actually know what x dot and z dot is. We can substitute it as 1/2 m, let's make it a bracket, x dot is actually the conjugate momentum, x over m squared plus pz over m squared plus mgz. This is now our Hamiltonian, which can further be simplified as h is equal to px squared plus pz squared all over 2m plus mgz. So where did this come from? So we can simplify it here, px pz squared all over m, and m squared, this is m squared, m divided by m squared, so mapupunta sa baba si m, and he will be joined by. So now we know that from our derivations earlier, the Hamiltonian equations are q dot is equal to the derivative of the Hamiltonian all over dpi, because it's generalized, and that the p dot is equal to the negative of the Hamiltonian all over dq. However, since this is projectile motion, it's two-dimensional, we can say that x dot is equal to Hamiltonian, the derivative of Hamiltonian with respect to px, and z dot is the derivative of the Hamiltonian with respect to pz, and then as well as this one, the p dot x is equal to the negative of the Hamiltonian over dx, and then p dot z is equal to negative of the derivative of the Hamiltonian with respect to the z position. Getting the derivative of all of these things, we already have this. Remember, we already got this from our here. See, we know that x dot is equal to px over m, and that c dot is equal to pz over m. That is why it's there. And then knowing this one, we know that p dot x is equal to the derivative of the Hamiltonian with respect to x. However, we don't actually have an x coordinate here. We only have a z, so this one becomes 0. And then this one is only concerned with mgz. This is then negative mg. So these are now our Hamiltonian equations. Since the coordinate x does not appear in H, it is therefore cyclic. So since x did not appear, it is cyclic. As a result, the conjugate momentum Px here is conservative. So that is it for the sample problem for Hamiltonian mechanics. Thank you, and if there is any question, please comment down.